John, how is your connection?
I think it should be good.
Okay.
If you guys can see something come up on the screen, let me know.
Answer to reviews GPCC group meeting 10/31/17, John.
All right.
This is what we expect to see.
Yes, that is what you
Okay,
should
good.
see.
So we are not surprised.
No, that's good. Okay. So I'm going to go over some of the major questions that reviewers had proposed to us on this round for this paper. And I guess there's a couple new people in the audience. A brief recap is we're looking at lead vacancies within perovskite materials. I guess, well, Svetlana, you were there in Telluride, so you heard initial little bit about what this was. So one of the first issues or questions that the reviewers had, excuse me, was regarding our explanation for what we thought about our defect state due to the vacancy and how it would be expanded across multiple momentum points within the system. And so they were not a fan of us just giving a verbal explanation, and so generating these band structures for the materials themselves of the perfect, which is in the blue lines, and then the initial vacancy after removing the lead atom is in red. And so what we were initially trying to describe to them was the fact that this defect state that we found is more or less going to be identical or maintain the same energy regardless of where in momentum space it was located. And so the main point is you can see that red line inside the band gap. It does show a little bit of energy shifting at the gamma point itself, but maintains a more or less relative energy throughout the system. One of the other interesting things from this plot itself is because all of our non-radiative calculations are done at the gamma point of the system, you can see within this 3x3x3 supercellular structure, the R point is the direct band gap, which is what it should be within the material. But because of this defect, you can see that within the valence band, there's now this raised up energy of these states and an increased spacing, making it closer in energy, at least to the top of the valence band at the R point. And so I'll talk about that a little bit in these next couple slides. And so one of the things that they really wanted us to do was to go ahead and use a K-point mesh to determine the electronic structures instead of just singling them out at the gamma point themselves. And so what I have here on the screen are two images comparing this 2x2x2 K-point mesh with the gamma point for both the vacancy and the perfect system. And so looking at the left image, we can see that increasing this K-point mesh is going to shift where the band edges lie and also shift where that vacancy state is exactly inside the band gap. And so the reviewers themselves had thought that they didn't think the defect state was going to change a whole lot or at all, and so it shifts just a little bit, but their main point was they didn't think it would stay within the band gap, which in this case it does. And so also one of the other things in looking at the perfect system, because we were taking the majority of our measurements or calculations at the gamma point, we have a band gap that's much too big relative to what the experimental gap is. And so you can see, again, with the addition of this K-point mesh, we are seeing a closing of the gap itself, and this migration of these band edges closer together, which would prompt a more realistic absorption and emission spectrum relative to experimental values.
John?
Yes.
Would it be correct, right or wrong, to say that the changes in the density of states and spectra that are contributed by K-points mesh are all appearing from the intrinsic states, while the dopant state stays at the same energy independent of the mesh. Would it be right or wrong?
Should be right.
I think, yeah, I would say that should be correct, because regardless of vacancy or not, you're going to see this migration of the band edges coming in. And so the vacancy state itself doesn't change a whole lot, but you see a similar modification to the band edges in both of the systems.
Thank you.
And so one of the other things we had discussed was, you know, what is the validity of this model, and what happens to band gaps when you start changing the size of the supercells. And so one of the things that this is from some work earlier done was dependent on the size of the supercell itself, the number of unit cells you're using, because of the band folding that can occur dependent on the number of unit cells. You can actually push back your direct band gap to the gamma point. And so that would allow us to then use a smaller unit cell as something that we could claim was the most realistic possible. And so I'm running this on two of our other models that we have. One was an REU that Dakota had used, so that should be done shortly. And then built also a 6x6x6, so just more or less doubling the unit cell we have now, with and without the central defect. One, to look what happens when you start expanding up into larger supercell regions away from a smaller cell, and also to have an idea of what might be happening in terms of being able to isolate this vacancy site even more so than it already is. And so hopefully when that finishes running, we'll be able to have an answer for a couple of the points that the reviewers were making. And so then
Actually,
the right image.
I have a question
here,
about your figure on the right.
Can I explain it first?
Oh, you didn't explain it yet?
Sorry, I was talking about the left image. So the figure on the right was an initial attempt by me in trying to account for absorption at multiple K points within the system compared to just what was at the gamma. Because what we were seeing was absorption images that weren't correct because we were missing energy ranges of transitions that might lie at different K points. And so the red line itself was when I had done absorption calculations at multiple K points and combined them, whereas the green was just for a gamma point itself. And so being able to account for the green gap that was at, you know, somewhere close to 650 was much more, the red line is much more realistic in terms of shape compared to the experimental absorption spectra that was seen.
Then here's my question. When you have a gamma point, you expect that you have less transitions, right? You expect that you're missing a few contributions because you're not including all K points. Then how you explain that your lowest energy peak is actually significantly higher for gamma point rather than for the when you include all K transitions? I would say this is a little bit, I'm okay with the high energy states, and because this is really, yeah, you re-establish some missed states, but here it looks like you losing the intensity, and this is a little bit counterintuitive.
Okay, so you're more or less worried about the relative intensities between the gamma and the multiple K points?
Yes.
At the onset? Okay. So these, they're not scaled, they're not normalized together?
No. You can, it doesn't matter, right? Because they're kind of normalized, because you can think about that you have your highest peak with red and with green being pretty much at the same energy, at the same intensity, right? So it means, in other words, ratio between your maximum peak in green versus first peak is much higher than the ratio between highest peak in red and the lowest energy peak in red. Like I'm comparing not just green and red, I'm comparing the ratio how much the big band around 500 electron volts changes with around 700 electron volts.
Mm-hmm.
So you would be happy if the heights of the green peak at 800 would be approximately equal to the red
but not larger.
At 700.
Right. Because here it looks like your green is twice of your highest band, right? But your red is what? Is one third, or even less than 1/3 of the highest.
Right. So
well, maybe they're not normalized. Maybe this is the issue of normalization. But I don't know. It looks a little bit strange.
And no, you'd be right. It's an issue of normalization because whenever I did this, I don't know, it was a year and a half ago. I'll show some more that includes multiple K points that have been done more recently.
Mm-hmm.
But this was just a first attempt to show that indeed including more K points does help the shape of the absorption look closer to that of experiment. That was more or less the bottom line for this itself.
John,
but I would agree that
were you dividing by number of K points for the red line, or it was an indefinite procedure?
Like the relative, what is it? There's a relative strength number inside, like the IB, the irreproducible file.
Mm-hmm.
I don't remember if I had done that when I made this image itself.
Okay.
Okay. So here is another illustration of trying to take into account all K points compared to just the gamma point itself. And so this one, this was produced by Dr. Interbev, and he figured out a way to solve the problem that I was having in generating some of these all together. And so this is for the system with the vacancy itself, the lead vacancy. And so you can see that when the initial onset changes slightly, when you get past 1 EV, you can see the all K points has a little bit more intensity, but then everything jumps up at a relatively higher level, and I believe that's largely in part due to taking into account all these other transitions and showing a more realistic spectra compared to what we initially had. Okay. So another thing that these reviewers were critical of was our treatment of the system with a spin polarized methodology, because we know that spin-orbit coupling is very important in these types of systems, but what we had up to date was not yet ready to handle the calculations for that, also just the amount of time that it would take. And so what we had done is now we have some of these spin-orbit coupling calculations done and comparing what happens to the band structures or the energy distributions of the states relative with and without the spin-orbit coupling. So on the left, you can see what looks like a normal density of states plot where you have a red-filled valence band and then a black line going higher in energy for that of just the standard DFT. But I put a blue line over top of it, and that's to show what happened, or no, that can't be right. Yeah. So the black line is the density of states, including spin-orbit coupling, and the blue line is that just with plain DFT. And so what happens is what we would also expect. You have a closing of the band edges, which is also seen in other calculations. But now, if you would take band gap values, instead of going from about 1 EV to close to 4 EV of having a large band gap of almost 3 electron volts, now you have something that runs from 3 EV all the way back down to a little below 1.5, and so the experimental is somewhere 1.65, 1.7 in that range. So the spin-orbit coupling definitely closes down the gap to what we would expect it to be. And so also showing the absorption for these values with and without the spin-orbit coupling. You can see that the initial onset's jumping from about 3 close to somewhere around 2 eV. So we're getting closer to the actual value themselves. And I think if we would even shift over one more to either one, include multiple K points with the spin-orbit coupling, or just take a single point spin-orbit coupling at the R point, you would see that band gap reduce even further, matching that of the experimental.
John?
I also, yeah.
So, what is your opinion about verbal addressing the criticism, even with this new data? Would you agree with the reviewer that it makes sense to completely abandon spin polarized calculations for the sake of spin orbit, or we still should be resisting and stubborn, telling that spin polarized DFT has some methodological value to analyze open shell configurations?
I guess I have mixed feelings. One, I think if we abandoned the open shell for the spin orbit coupling, I mean, I think it would be almost more readily accepted by people in the community, especially given what I kind of feel is strong language from the reviewer and completely dismissing our notion of trying to use spin polarized calculations. Mm-hmm. I don't know. I mean, but on the other hand, I do think, given that, and we have the data produced already, I don't know. I mean, there could be something useful, at least to have it put out there, so that I mean, we don't have to come back and possibly do it again in the future, or if someone else is just interested in something a couple of years down the road, that there might be some value in it.
So can we distinguish singlet, doublet, triplet, and quartet density of states in the density of states with spin orbit?
Me personally, no. And I would guess probably, well, the answer is no, because it's all.
And with
no.
spin polarized, we can, more or less.
Yes.
So yeah. It is, even if you accept criticism of reviewer and give new data, we should probably tell that we see evident benefits from spin polarized calculations in general. Okay.
Right. And so on this last slide, I don't know if it's a little bit hard for you to see. So this, on the very right-hand side, I'm going to work backwards. On the very right-hand side is the same thing. It's the density of states with and without spin orbit coupling for the vacant model. And so, again, you see something similar. You see with the spin orbit coupling added, and this goes back to your earlier question about, do we think that the band edge is moving is relative to the intrinsic versus the vacancy state? The intrinsic bands move in, and the vacancy state itself stays relatively in the same position.
Our call will be disconnected.
So you have a shrinking of the band gap